There is a fleck of paint orbiting the Earth right now, no bigger than the tip of your finger, and it is moving at something like 10 times the speed of a rifle bullet. At that velocity, physics stops behaving the way your intuition expects. That harmless little chip of paint carries roughly the energy of a hand grenade. It has already, in real recorded incidents, gouged craters into the windows of spacecraft. Now scale it up. A bolt, a shard of aluminum, a dead satellite the size of a bus, tumbling silently end over end, with no engine, no radio, and nobody at the controls. There are more than 35,000 objects large enough to be tracked circling our planet, and millions of smaller fragments that are too small to see, but plenty big enough to kill. Every one of them is a bullet, and we are adding thousands more every single year. Here is the nightmare scenario that keeps space agencies awake at night. It has a name, the Kessler syndrome, and the logic is horrifyingly simple. Two objects collide. That collision shatters both into thousands of new fragments. Those fragments spread out and go on to hit other things, creating tens of thousands more fragments, and the cascade feeds itself faster and faster until the most useful orbits around Earth are wrapped in a shell of shrapnel so dense that nothing can safely fly through it. No new satellites, no space station, no GPS, no weather forecasting, no satellite communications, no launches. Humanity locked out of space by its own garbage, potentially for generations. That is the problem China says it wants to solve with a laser. The idea sounds like pure science fiction. A station in orbit that spots a piece of debris, locks on, and fires precisely timed pulses of light at it until the fragment's path bends and it falls harmlessly into the atmosphere to burn up. Chinese researchers have modeled exactly that and published the work. But here is the part almost nobody in the West registered, and it is far more remarkable than the laser. Because while the laser is still, honestly, a research project, China has already done something in orbit that only one other country on Earth has ever pulled off. In January of 2022, a Chinese spacecraft quietly crept up on a dead satellite drifting 36,000 kilometers above the equator, physically docked with it, fired its engine, and dragged it thousands of kilometers out of the way. They did not simulate it, they did it, and the entire world watched it happen through telescopes, because you cannot hide something like that. Today, we are going to walk through the real scale of the debris crisis, why cleaning it up is far harder than it sounds, how a laser could actually push a piece of junk out of the sky, what China has genuinely built versus what is still on paper, and the uncomfortable question sitting underneath all of it, which is that a machine capable of moving a dead satellite is, by definition, capable of moving a live one. Before we get into it, if you enjoy videos like this, hit the like button right now. These take a serious amount of research and time to put together, and every like pushes this video out to more people who would love it. Subscribe as well, so you never miss what we cover next. Let's get into it. To understand why anyone would point a laser at the sky, you first have to understand just how bad the situation up there has become. Everything humans have launched since 1957 that did not come back down is still up there in some form. Spent rocket stages the size of school buses, satellites that died decades ago and simply kept going, bolts, lens caps, insulation blankets, and clouds of frozen coolant, and crucially, the debris from things that have already broken apart. The reason all of this is so dangerous is orbital speed. To stay in low Earth orbit, an object has to travel at roughly 28,000 kilometers per hour. Everything at that altitude is moving at approximately that speed, in whatever direction its orbit dictates. So when two objects meet, they can meet head-on at a combined closing speed of tens of thousands of kilometers per hour. At those velocities, mass barely matters. Energy scales with the square of speed. A 1 centimeter fragment hitting a satellite is comparable to being struck by a small exploding shell. There is no armor that helps. The satellite does not get dented. It gets destroyed and turned into thousands of new fragments. And we have already watched this happen. In 2009, a defunct Russian satellite slammed into an active American communications satellite over Siberia, the first major accidental collision between two intact satellites, and instantly created thousands of trackable pieces of debris that are still circling the planet today. Deliberate destructive tests over the years have made things dramatically worse, each one scattering enormous quantities of long-lived fragments into busy orbits. Now layer on what is happening right now. We are in the middle of the largest expansion of satellite launches in history. Mega constellations, with thousands upon thousands of satellites, are being deployed by multiple companies and multiple countries, including China, which is building its own enormous constellations. The population of objects in orbit is climbing steeply, and every additional object is both a potential victim and a potential source of new debris. The result is that satellite operators now regularly have to perform collision avoidance maneuvers, burning precious fuel, and every drop of fuel spent dodging is a drop not spent, extending the satellite's working life. Space agencies have warned that things will get worse before they get better. So the world has arrived at an uncomfortable conclusion. It is no longer enough to stop making new debris. Someone is going to have to go up there and start cleaning, which sounds straightforward until you look at what it actually involves. The instinctive reaction to space junk is to imagine a garbage truck in orbit, a spacecraft that flies around scooping up debris and hauling it away. That mental picture is completely wrong, and understanding why is the key to this entire story. The first problem is that orbit is not a place. It is a speed. Objects in orbit are not floating in a fixed location you can drive to. They are falling around the Earth at enormous velocity, and every single one is on its own path, at its own altitude, at its own angle. Two pieces of debris that appear close together on a map may be in wildly different orbits, and to move from one to the other, you do not simply steer, you have to fundamentally change your own velocity, which costs an enormous amount of fuel. Changing the tilt of your orbit is especially brutal. A spacecraft carries a strictly limited amount of propellant, which means in practice, one cleanup mission might only be able to reach 1 or 2 targets, ever. The second problem is that debris does not cooperate. A dead satellite is what engineers call an uncooperative target. It has no power, no communications, and no way to hold still. Most of them are tumbling, often spinning on multiple axes at once, sometimes because a fuel leak or an earlier impact set them spinning years ago. Now, imagine trying to grab something the size of a bus that is cartwheeling unpredictably in a vacuum, while both you and it are traveling at 28,000 kilometers per hour. And if you get the approach wrong, you do not just fail, you collide and create exactly the catastrophe you came to prevent. The third problem is that these objects were never designed to be caught. A modern satellite might be built with a docking plate or a grapple fixture for future servicing, but the debris causing the most concern is decades old, launched at a time when nobody imagined anyone would ever come back for it. There is no handle. There is nothing designed to be gripped. You are improvising a way to seize a spinning, fragile, irregular object that may fall apart if you grab it wrong. And the fourth problem is scale. Even if you solve all of that, you're still removing objects one at a time at enormous cost from a population of tens of thousands. That last problem is exactly why lasers entered the conversation, because a laser does not have to chase anything. Light travels at the speed of light, and a laser can, in principle, engage target after target after target without ever moving from where it sits. The idea of moving space debris with a laser sounds like something from a movie, and the common assumption is that the laser vaporizes the junk, blasting it into nothing. That is not how it works at all, and the real mechanism is much more elegant. The technique is called laser ablation, and here is the principle. You fire a very short, very intense pulse of laser light at the surface of the debris. That pulse does not destroy the object. It heats a microscopically thin layer of the surface so rapidly that a tiny amount of material instantly vaporizes and shoots away as a small jet of plasma. And because every action has an equal and opposite reaction, that little jet of escaping material gives the debris a nudge in the opposite direction. One pulse produces an almost imperceptible push, but fire pulses repeatedly, many times per second, over minutes, and those tiny nudges accumulate. You're effectively turning the surface of the junk itself into a miniature thruster, using light delivered from a distance as the fuel, and you do not need to push it very hard. This is the beautiful part. To remove a piece of debris from low Earth orbit, you do not have to blast it away or knock it into the sun. You only need to slow it down slightly. Shave a little velocity off its orbit, and the low point of that orbit dips deeper into the wisps of atmosphere at the top of the sky. Atmospheric drag, then, does the rest of the work, gradually pulling it lower over subsequent orbits until it re-enters and burns up harmlessly. The laser does not destroy the debris, it just tips it over the edge and lets the planet's own atmosphere finish the job. Chinese researchers have taken this concept seriously and modeled it in detail. A team associated with an Air Force engineering university in Xi'an published simulation work exploring an orbital laser station designed to clear small fragments, the sub-10 centimeter pieces that are too small to reliably track and dodge, but easily large enough to destroy a spacecraft. Their modeling examined aligning on a target and delivering rapid, repeated pulses to alter its orbit or push it into the atmosphere. And this is not a uniquely Chinese idea. Proposals for ground-based and space-based debris lasers have been published by American, European, and other researchers for decades. But here is where honesty matters. And I want to be very clear with you. That work is simulation and research. It is a modeled concept, not a deployed machine sitting in orbit erasing junk today. Anyone telling you China has an operational debris zapping laser station up there right now is getting ahead of the evidence. What China does have, however, is something genuinely operational and genuinely world-class, and it is the necessary first half of the problem. Before you can remove a piece of debris, you have to be able to find it, track it, and predict exactly where it will be. And that turns out to be a monumental challenge on its own, because you are trying to spot a dark, non-reflective object the size of a coffee cup, hundreds or thousands of kilometers away, moving at 28,000 kilometers per hour. Here, lasers are already doing real work, not as weapons, but as measuring instruments. The technique is called laser ranging, and it works exactly like a police speed gun, scaled up enormously. You fire a pulse of light at the object and measure precisely how long it takes for a few photons to bounce back. Multiply by the speed of light, and you know the distance with extraordinary accuracy. This is where China has quietly built genuine world-class capability. Researchers at the Shanghai Astronomical Observatory have demonstrated debris laser ranging with sub-decimeter precision, pinpointing the position of a piece of orbital junk to better than 10 centimeters, using rapid picosecond laser pulses. To appreciate how absurd that is, they are determining the location of a tumbling scrap of metal hundreds of kilometers up, moving at hypersonic speed to within the length of your hand. European teams have pushed the same technology forward, including the difficult feat of ranging debris in broad daylight rather than only at night. And Chinese researchers have gone further, publishing designs for constellations of dedicated tracking satellites, proposals for networks of small spacecraft in low orbit that could between them track the overwhelming majority of debris targets every single day, building a live, continuously updated map of the junk cloud. Put those two capabilities side by side, and the strategy becomes clear. World-class laser tracking that can pinpoint debris with extraordinary precision, and published research into laser systems that could nudge that debris out of orbit. One is real and operating now. The other is on the drawing board. Together, they describe a country that is methodically building toward the ability to find and remove objects in space. But none of that is the most impressive thing China has done, because while the laser stayed on paper, something else went to orbit, and it did not push a piece of junk with light. It reached out and physically grabbed it. In October 2021, China launched a spacecraft called Shijian-21. Chinese sources described it plainly as a space debris mitigation satellite. No detailed specifications were released, and then, for a few months, it did something extraordinary in full view of the world's telescopes. The reason we know exactly what happened is worth appreciating. Geostationary orbit, that ring 36,000 kilometers above the equator, is watched continuously by commercial space tracking companies and by the U.S. Space Force. Nothing large moves up there without somebody noticing. So when Shijian-21 began performing sophisticated rendezvous and proximity operations, carefully maneuvering near other objects, independent trackers followed every move. Its target was a satellite called Beidou 2G2. That spacecraft was part of China's own navigation system, launched in 2009, and it had failed almost immediately. It had been drifting uselessly ever since, and analysis of its behavior suggests it had suffered a collision and fuel leaks that left it tumbling. It was, in every sense, a dead piece of junk sitting in one of the most valuable and crowded orbital regions in existence. In late December 2021, Shijian 21 approached it. It matched the dead satellite's orbit, closed the distance, and docked with a tumbling, powerless spacecraft that had absolutely no docking equipment and no ability to help. Then, on January 22, 2022, it fired its engine in a single large burn and towed the dead satellite up and out of the geostationary belt, depositing it roughly 3,000 kilometers above the crowded ring. That is far higher than the standard graveyard orbit, which sits a few hundred kilometers above GEO. It did not just move it out of the way, it put it emphatically out of the way. 4 days later, Shijian 21 undocked, left the corpse in its new disposal orbit, and returned to geostationary orbit itself. Analysts speaking at a public webinar hosted by American think tanks laid out the tracking data, and the assessment was blunt. This demonstrated a capability that, until then, only the United States had shown. It is comparable in kind to American commercial servicing vehicles that have docked with satellites to extend their lives, with one crucial difference. Those American missions docked with live, cooperative, functioning satellites in planned commercial operations. Shijian 21 docked with a dead, uncooperative, tumbling one, and China has kept going. A later spacecraft, Shijian 25, has been involved in rendezvous and docking operations in geostationary orbit that observers assess to include an orbital refueling demonstration, transferring propellant to another satellite in space, something that would extend satellite lifespans enormously. At an International Astronautics Congress, a senior Chinese space official publicly stated China's intention to develop active debris removal capabilities. So the honest scorecard is this: the laser is research, the tracking is world-class and operational, and the ability to physically approach, capture, and relocate an uncooperative object in orbit has been demonstrated in space and independently verified by outside observers. Which brings us to the uncomfortable part. Here is the tension at the heart of this entire subject, and it is not a conspiracy theory. It is discussed openly, in public, by Western think tanks, by space policy researchers, and in mainstream space journalism. It comes down to one sentence: a spacecraft that can quietly approach, grab, and move a dead satellite is, by its nature, a spacecraft that could quietly approach, grab, and move a live one. The technical term for this is dual use, the exact same capabilities that make an excellent debris removal vehicle, the ability to find a target close in without being detected until late, match a tumbling object's motion, physically attach to something never designed to be attached to, and then change its orbit, are the capabilities you would want for interfering with someone else's satellite. There is no engineering difference between a tow truck and a repossession vehicle. The difference is entirely in the intent of whoever is driving it. And this concern is not aimed uniquely at China. It applies to every nation and company developing these systems, including American, European, and Japanese ones. The United States has flown servicing vehicles that dock with satellites. Europe is preparing missions to capture debris with robotic arms. Japan-linked companies are developing capture technology. A defense research agency in the United States has been working on robotic servicing spacecraft of its own. Everyone building this technology is building something dual use, and everyone knows it. What makes it fraught is the combination of capability and opacity. When a spacecraft's specifications and mission objectives are not published, outside observers are left to infer intent from tracking data alone, watching where it goes and what it approaches, and guessing why. That uncertainty is where mistrust grows. Analysts writing about China's debris efforts have repeatedly landed on the same conclusion. The technology itself is genuinely valuable, and the debris problem is genuinely urgent. And whether these programs are ultimately viewed as responsible stewardship or as a strategic threat will be determined less by the hardware than by transparency. The same logic applies to lasers, which is precisely why the topic makes people nervous. A laser powerful and precise enough to nudge debris is a laser that could, in principle, be pointed at something nothing functional. Again, this is a general property of the technology, not a uniquely Chinese one. It is one of the main reasons debris removal lasers have remained largely in the research stage worldwide for decades, despite the idea being proposed as far back as the 1990s. The physics has never been the only obstacle. The politics has always been part of it. So the world faces a genuinely difficult situation, a real and worsening crisis that urgently needs solving, and the only tools capable of solving it are tools that make everyone nervous about each other. Here is the encouraging part, and it deserves airtime because this is one of the few frontiers where nearly everyone actually agrees on the goal. China is far from alone in this. The European Space Agency has a dedicated mission designed to rendezvous with a piece of orbital debris and capture it using a robotic claw with multiple articulated arms, closing around the target like a claw machine before dragging it down to burn up in the atmosphere. A company operating out of Japan and the United Kingdom has already flown demonstration missions, including successfully capturing a piece of simulated debris in orbit using a magnetic docking system, and has been developing missions to capture genuinely old, uncooperative junk with a robotic arm. Other companies and agencies are pursuing nets, harpoons, drag sails that unfurl to increase atmospheric drag, and contactless methods that nudge debris using ion beams or electrostatic forces. Alongside the hardware, the rules are tightening. Regulators have moved toward requiring satellites in low orbit to deorbit themselves within a few years of finishing their missions, rather than lingering for decades. International bodies have been working toward zero debris standards. Patent activity in debris removal has accelerated sharply in recent years, signaling that this is moving out of the research phase and into pre-commercial development, an actual industry forming around cleaning up the sky. And the reason everyone is converging is simple. Orbit is genuinely shared. Debris does not respect borders. A fragment created by one country's satellite breaking up will, over the following years, threaten every other country's spacecraft. There is no version of this where one nation solves the problem for itself alone, and no version where one nation can be protected from everyone else's mess. It is a commons, and it is filling up with shrapnel. So this is a strange, uneasy race, a competition to develop capabilities that everybody needs, that everybody is slightly afraid of everybody else having, aimed at a problem that will hurt all of us equally if nobody solves it. Step back, and the significance here lands on 3 levels. Practically, this is one of the most genuinely important technical challenges of the next few decades, and it is badly underappreciated. Almost every part of modern life quietly depends on satellites, navigation, weather forecasting, banking timestamps, shipping, agriculture, disaster response, communications, and the internet itself in many places. That entire invisible infrastructure sits inside a shell of debris that is slowly getting denser. Solving this is not an environmental nicety. It is the maintenance of a system civilization now runs on. Strategically, the pattern here should look familiar if you watch this channel. The foundational ideas, laser ablation, robotic capture, debris ranging, were developed by researchers across the United States, Europe, and Asia over decades. But China has moved with characteristic speed from research into demonstrated capability, putting a spacecraft in orbit that physically captured and relocated a dead satellite, while much of the world's effort remained at the proposal and prototype stage. Whether the laser concept follows the same path from paper to hardware is the question worth watching over the next decade. And ethically, this is a genuinely hard case with no clean answer, which is exactly why it is worth thinking about, rather than sloganeering about. The technology humanity needs to save its own orbits is inseparable from the technology that makes rival nations distrust each other in space. You cannot have the cleanup crew without also having something that looks, to a nervous observer, like a threat. The only real solution anyone has proposed is not technical at all. It is transparency, verification, and shared rules, agreed before an accident or a misunderstanding forces the issue. So where does that leave us? With a sky full of bullets that we put there ourselves, with a genuine physics-backed plan to sweep some of it away using nothing but precisely aimed light, with a Chinese spacecraft that already proved in front of the whole world's telescopes that it can sneak up on a dead satellite and haul it away, and with an unresolved question about whether the machines built to clean up space end up making it safer, or just make everyone more afraid of everyone else. The junk is real. The crisis is real. The technology is arriving. What is still missing is the trust to use it. If you enjoyed this, hit the like button and subscribe so you're here for the next one. It genuinely takes a huge amount of research to put a video like this together, and your support is what keeps this channel going. Now, I want to hear from you, because this one genuinely splits people. Orbital debris is a slow-motion disaster that could lock humanity out of space for generations, and lasers and capture spacecraft may be the only realistic way to clean it up. So the countries building them are doing something the whole world needs. On the other side, the very same machine that tows away a dead satellite could, in principle, be used against a working one, and that makes a lot of people deeply uneasy, no matter which country is flying it. So tell me where you land. Should we be building this technology as fast as possible because the debris crisis is urgent, or slowing down until there are real international rules about who can grab what in orbit? And be honest, before this video, did you have any idea how much garbage is flying over your head right now? Drop your answer in the comments below. I read every single one.